Thank you so much, John, for the very nice introduction, and thank you, Milton, for the invitation. You are right. More and more women are postponing motherhood, but the main reason for doing that is not so much for career. It's because, unfortunately, there is a shortage of men that are deemed suitable for women to marry.
With a man.
Right. And in fact, we published 2 or 3 papers in the last year on why is this happening, and the main reason is that women don't marry down, they only marry at their level or they marry up. And there are more women than men that are getting a college degree. So 4 women every 3 men, therefore there is a shortage of, like you said, good men. And that's a social demographic problem that is going to become only worse and worse if we don't are able to find a solution. So therefore, freezing vitrification of eggs can be a solution to try to buy time, but it's probably a little bit deeper than what I just revealed to you. So let's go to my topic. First, I want to disclose that I'm a co-founder and medical advisor of the company Fertile Safe, which also sponsored the studies on automatic vitrification. Now, there is no doubt, like Anna Cobo has showed to you, that vitrification is definitely the best thing to do in terms of cryopreservation. And in fact, the results on probability of live birth based on the number of oocytes are definitely much higher than the old technology of slow freezing. So that's not an issue anymore. However, as Anna has expressed very clearly, there are not too many Anna Cobo around, there are not too many Michael Tucker around, so we cannot clone them. Therefore, there are differences in the skills of embryologists doing the same process of vitrification, as was written in this article by Esther Tan in Canada. And you see here that the 3 embryologists were freezing vitrifying eggs. So embryologists 2 were a senior, 1 was a junior. So the 2 senior froze 14 eggs, 12 eggs. The junior embryologist vitrified 17 eggs. And then years later, 7 years later, this patient went back to use the oocyte. And you see the survival rate among the 2, between the 2 senior embryologists. One had a survival rate of 71%. The second senior had 17%, very, very dismal result. And these are the same patient eggs, okay? It's not a different donor or a different patient. And the third one is 70%. So really a lot of variability, like Anna Cobo was saying. So therefore, there are definitely problems with the vitrification that need to be bypassed, that need to be standardized. One is that is a time-consuming. I'm not going to belabor on the osmotic and the chemical toxicity over the concentration of a cryoprotectant, the possibility of mechanical damages, the fact that you really require a skilled personnel. It's not, in the old days was, oh, vitrification is so much simpler than doing slow freezing. Well, that's not really true. And therefore, particularly the control on the rate of cooling and, most importantly, the rate of warming are really crucial for survival and usage of the vitrified eggs. Therefore, there is a lack of standardization. There are so many different protocols, and that's what really makes the result non-reproducible, more than just thinking about some particular patients. They may not really do a good job in vitrification. But these are really the main problems that we can identify. And then there are different carriers. These are just a small sample on how many different devices are available to carry out the process of vitrification, Vitrifeed, CBS, Cryolock, and so forth. It's just a small sample. And do they all perform in the same way? Well, the answer is no. If, we did a study here to measure the degree of cooling rate according to sound, and you see that different device, different carriers, they have a different degree of cooling rate. And for example, the Cryolock, 18,000 Celsius per minute, the EVIT, which is the device of Fertile Safe, 20,000, cryotop 29,000. And to have an optimal cryo rate, it should be 20,000 or more. So in this case, these are probably the best carrier for the open system. So the ideal situation here is to create an automatic vitrification device, but it should have this type of requirements. It should be a device where you can achieve cooling and warming rates that are in excess or equal to 20,000 degrees Celsius per minute. The volume on the cryo carrier should be really very, very small, the so-called minimal drop size, so less than 0.1 microliters. Should be easy to operate. Should automate all the vitrification steps, including plunging in the liquid nitrogen. So the embryologist should not do nothing else than just load the eggs in the vitrification device and then let it go until the process is completed with the plunging in liquid nitrogen. And also automate the warming steps to avoid the mechanical damage, not too long to complete the entire processes, and should be ideally a system that can be applied on whether you are using open or closed systems. And the storing the samples should be in standard liquid nitrogen tanks. You don't want to buy completely different storage devices. We should be really try to use what you already have. So there are available products already on the market, at least if not publicly commercially available. They are in the research stages. One is from Gary Smith, the so-called microfluidic device, where you just load the eggs in this device, and then different channels through which you can slowly add the different culture media for different vitrification steps. Then there is the product of Genea Biomedics. It's called Gavi, and this product has been around now for quite some time, and that's the way that it looks like. The cartridge, where you just load in this cartridge the eggs or the embryos, although it's been working more with embryos than with eggs, and then the computerized system moves this cartridge among the various stations. But then you still need to have an embryologist that at the end of the process takes the cartridge and goes and put it in the storing. And the storage is also different in your liquid nitrogen tank. So you need to change a couple of routines in your IVF lab. These are some initial results from the 2004 study of the Gavi. And you see that here they use the embryos, mice embryos. But I just want to point out that what they published in terms of cooling and warming rates, they are below the 20,000 Celsius that are supposed to be the best in terms of final outcome. But nonetheless, it's one of the devices that it's already available on the market. What we've been working on is a device that is called Zahra, and is a device that you see here is composed of a screen where you can load the protocol that you want. And let me show you how is really the key component of this device. This key component are straws, and the straws they have a particular capsule at the end of it. So you load your embryos, you load your eggs, you load your ovarian tissue, you load testicular tissue, whatever you want to do automatically vitrification. And then after you load in the straw, you insert at the end of the straw these capsules that has 50 microns square holes. You can see here bovine oocytes, for example, that are sitting on this mesh. And then the way that I want to show the video there, if it's possible to go back. Yes, thank you. So that's after, after you load it, you just insert the capsule at the end. And now after you insert the capsule at the end, what you do, you just put every single straw, and you can put up to 6 straw, yes, in this cartridge. And then this cartridge here is now going to be loaded in the machine. And you can see that here are vertically positioned the cartridge. Here is the mini straws for the eggs. Here are maxi straws for ovarian tissue or for testicular tissue. And then what you do, you start the process. As I told you, there is a display where you have programmed already what you want for various times in the various stations. So you do the programming here. And after you do the programming, you see in a moment that the machine starts the automatic processing. So that's the way that I told you before. You have the cartridge right here. So that's the very first initial steps. And you see that once the program is activated, there are different caps here. They have a different vitrification solution. Yes? And then the system rotates, and after a particular time, because you have a program, how much time you want, for example, in the first station, how much time you want in the second station, so the device rotates, and it goes now in the second cap, okay? Goes in the second cap, and then it plunges down, stays for the time that you have already programmed, and then before it goes to the next one. And then what is important is that during the time that the stations move around, we notice that the fact that the embryos or the eggs, they have the opportunity to go up and down, yes? And this physiological mixing of the eggs or the embryos during the various rotation is probably a very important phenomenon, not to be stable. It's not a static mechanism, but it's a dynamic mechanism. And here is the slide just to show you in this short video part that we want to complete the process. We don't want that the embryologist has to leave everything that he or she is doing and run because now the program is over, because this is the very last station where there is a paper, special paper at the bottom of this cap to dry and do the minimal drop size. Okay, that's the paper. But now you plunge everything in liquid nitrogen, because here is where the liquid nitrogen is, and then the system beeps, alerting the embryologist that the process is completed, and now you can go take the cartridge, and then you go and do your own storage in regular liquid nitrogen tanks. Okay, so the machine waits for you because here is liquid nitrogen. Okay. Now we use the open system, so there's always a comment. Well, but open system, the liquid nitrogen, it's probably potentially contaminated. What we use a clean liquid air, which is produced by this device that is called the CLAIR. Clean liquid air. And if I can have the small video also on this one, if you can click it for me, you see that it takes about 10 minutes to have a clean liquid air produced. And essentially, to explain to you how this device works, you see here there are two containers, one on the outside, one on the inside. There is a filter here, okay? And this filter, between the first and the second compartment, we have liquid nitrogen that has been inserted here so that can cool the very first one. And the first one, by aspiration over the volume of the liquid, over the air that you have in the room where this device is positioned, by cooling the air by contact, so the air is filtered, goes inside the container here that is metallic container, and is very, very cold. It liquefies your air, and then you open the sink, and then you collect your clean liquid air, which is exactly the same physical chemical characteristics of the liquid nitrogen, but the difference is it is clean. So we tested many times with the company that does the microbiological assessment, and it's completely clean and sterile. So what are the results so far of what I've been telling you? We've been publishing studies with mice, bovine, embryos, oocytes. Later we published also with ovine, and I will show you some of those. So here are just the protocols that we have used for the vitrification and the rewarming. And by the way, when you saw the machine going in the directions toward the liquid nitrogen as a final stop, you can also program the machine in the opposite direction, starting now from the vitrification stop and going in the other direction. Now you're doing the automatic rewarming. So you took your straw from the liquid nitrogen, you put it in the tank, you put it in liquid nitrogen, and now from there, in the warmed plate, you do the opposite direction, and then you do the rewarming steps, okay? So here are the protocols that we've utilized for vitrification of mice and bovine oocyte and embryos, and here the protocol for the rewarming. And let's look at the result. Here are the results with mice, oocyte, and embryos. Originally, the number of eggs were 40, 95% survival. Viability was 100%. These are the 8-cell embryos we vitrified with the Zahra 35. This is 94% the survival. And then 33 out of 35 developed into blastocysts, and 28 out of 35, they also hatched. So very good results. And then here we have the bovine oocytes. We vitrified 84 oocytes in bovine, 61 survived, 73%, compared to the fresh 83%. And here you have the fresh zygote versus the vitrified zygote. And you can see here also a good survival for the bovine oocytes. And then, as I told you also recently, we did ovine. Also here, good survival, 90% oocyte survival. And of the oocyte that survived, 60% cleaved to reach the more than one blastocyst stage. And therefore, even with the ovine, we can reproduce the results. Now, if you compare the three devices that are on the market right now, except this one is still in our prototype stage, you have the Zahra that takes about 17 minutes to complete, while the Gavi, if you do the Gavi, it takes about 37 minutes to complete. In 37 minutes, you do 4 oocytes for Gavi. In 17 minutes, you can do up to 30 eggs per Zahra, because you can put, as I told you, 5 eggs per straw. You have 6 straws, so those are 30. What else are we doing in terms of material for studying? So what you're doing, and this has been recently published, work done in collaboration with Sergio Ledda in Sardinia, is vitrification of in vitro produced ovine embryos, no eggs now, we are talking about embryos. And here they are really experimenting on what's the ideal number of steps, what's the ideal number of solutions that are required in order to maximize your outcome. And in this study, the embryos of ovine, they were used in either multi-step, so 8 steps, yeah, with different equilibration solution, versus the 2 steps. And this study was also done to introduce to you another concept that, yes, you can have an automatic vitrification, so you don't do anything manually, except loading the eggs or the embryos or whatever tissue in the straw, and then you leave everything to the machine. Or if the concept of reproducibility is to make sure that there are minimal errors during moving eggs from one solution to another one, well, I can just use the straw with that capsule at the end and use the straw and manually put it towards the different solutions, see? So this is called the EVIT, or easy vitrification. So I don't need the machine, but I just need the straw with that capsule at the end. And by using that system, now I can move all at once, 5 eggs at once, 5 embryos all at once among the different solutions that I've now prepared already. And this study really proved that it's extremely reproducible, extremely successful to do it. And you see here that the survival rates after 24 hours of a post-warming culture in the ovine embryos, it's the same 56%, whether they are in a multi-step or in 2 steps. But if you have expanded blastocyst, it's much better to do a multi-step vitrification rewarming than not the 2 steps. This also has been very recently published. Additional studies with human ovarian tissue. So we've been seeing that the survival of the tissue after has been vitrified in the maxi straw of Zahra, exactly the same if you do it manually. And then we have vitrification of testicular tissue. You can recognize now the straw, the capsule, and these are the seminiferous tubules that are now floating into the straw, and then it goes again perpendicularly in the vertically in the machine, and they are going to be frozen. And in terms of survival of the testicular tissue, it shows how this testicular tissue by the Hochst vital stain, it's showing a very good survival after has been rewarmed. And another concept that comes together with the opportunity of vitrifying and rewarming in a straw is, okay, particularly for the veterinarian market, but you know, we can start with veterinarian and then we perhaps can move it into the human field, is, you know, if I can do this in a straw, is it important to remove everything from the straw and then reload it in another catheter and then do the transfer away? The veterinarian people say, no, we know what we can do, because they want to try to save money as much as possible. We can use the same straw that you are using to do the vitrification and the rewarming, and then I'm going to use the same straw and I inseminate the cow. So don't move anything out of that straw, and we can do the insemination in the cow, okay? So that concept took also the attention of people that are in the breeding industry for horses, and now they are using the system of easy vitrification with a long catheter, and they are inseminating, doing the transfer of embryos into horse. And then, of course, if that's possible in cow, it's possible in the animal industry, perhaps we could propose that if we do the vitrification of human embryos with the easy vitrification method, perhaps we also can do it, do the embryo transfer in human. So summary and conclusion, we have shown, I tried to show you that it's possible. Automation is really coming, is already probably here, to vitrify oocyte, embryo, tissue slice, and the importance of the cooling and warming rates of 20,000 degrees Celsius or more. The efficiency can do up to 30 eggs at once, or embryos, or 18 slice, because you need to put less slice for the ovarian tissue. Automatic insertion into liquid nitrogen, the possibility that one device can do both vitrification and rewarming, and this perhaps is the only way to reproduce the results and standardize results across many centers that are doing vitrification. So this is my last slides, for the thank you slides for Milton, for the group in Australia, and then collaboration with Paolo Levisetti from Milano, and the group in Sassari, Sardinia, that has been doing a lot of work with the ovine eggs and embryos. Thank you so much.
Thank you. We're right on time, so we have 10 minutes for the discussion.
So Pasquale, that was a chilling talk.
Thank you.
The most revolutionary imaging in electron microscopy has been achieved by a technique known as quick freeze deep etch. And I'd like to discuss with you 4 advances that this electron microscopy method works with. Number 1, it's using liquid helium, so much colder. Number 2, it uses quenching with either propane or freon, even instead of the liquid nitrogen, so that when you put something into liquid nitrogen, initially you get a gas bubble of nitrogen around it. And the virtue of having freon or propane that's a liquid, even at liquid nitrogen temperatures, is that it doesn't bubble, it doesn't form bubbles, so that you can quench it and freeze it much faster. It's used in intermediary metabolism as well. So liquid helium, quenching. Also in electron microscopy, they use high pressure, and the pressure seems to preserve structure. I don't know how you do that with this system. But the last thing is they have cells attached to sapphire cover slips. And the temperature cooling through sapphire is much faster than glass. And I think if your eggs were attached to a substrate, that, I know it's different than having it liquid, but as a substrate, you'd have virtually no liquid, and there might be methods to, in a sense, have it attached the whole time along. So if I can get an internet, I'll show you an image of it in my talk. But I'll talk to you more about it.
Thank you.
You'd be truly frozen.
Thank you for the comment. Klaus?
Klaus,
Yes,
yeah.
Klaus.
Very good, Pasquale.
Thank you, Klaus.
I enjoyed your talk very much. I have some things I would like to discuss with you. So you have explained to us that a cooling rate of 20,000 degrees per second is very...
Per minute.
Per minute. Is very important. So what is the actual evidence for that?
The actual evidence are studies with that Amir has carried out by using different devices and how the survival of eggs and embryos have been reported. If you have, let's say, 1,500 Celsius versus 5,000 versus 10,000 versus 15,000.
It's very difficult to calculate the actual cooling rate.
Yeah.
We agree that the interesting thing is the cooling rate in the cell or in the embryo or whatever we are cooling.
Yeah.
But of course, this will depend on the size
Sure.
of what you're looking at. So ovarian tissue, and as you showed us, testicular tissue, will have a lot lower cooling rate. But they still vitrify. They still do okay.
Yeah, and that's why you do it very, very small pieces and very thin and
They are
yeah,
much bigger than
yeah.
the embryo and the oocyte anyway. So the cooling rate will be a lot lower in these. So I just wonder whether these 20,000 is the magic number.
Well, the magic number came because, as I told you, they were different temperature for different experiments. And in terms of survival, viability, and future hatching of blastocysts, that's the temperature that was deemed to be the most effective. For eggs and embryos,
Yeah. It probably also relates a lot to the way that the device is actually made.
Yeah, possible. Yeah.
All right?
Yes.
I am Dr. Pai from Mumbai. I have done more than 80,000 embryos in the last 10 years. So what I wanted to ask you is 3 questions. One is that I'm always scared of automation. What if the machine stops? So how much time would you experiment it before putting it into the market? How many hours would you prove that it will not stop? Because one stop can finish you.
Sure, but there is an alarm system if the machine stops, so that beeps. Yeah.
And it hangs. Because recently I look at the US that automate, like in our system,
Yeah.
I use mechanical filling of the embryo. Every Tuesday and Friday the tanks are filled mechanically because I'm
Yeah.
always worried. Somewhere something, if it goes wrong, 20 years down the line, I can lose everything that I earn. So I'm very scared of the automation part because one
Sure.
mistake. Look at Johnson yesterday. They are given $8 billion. $8 billion yesterday. The news has come out. So how are you going to protect litigation?
Yeah. So that's one question. So the question that you have is very important. Of course, you need to have checkpoints built into the system. But, there are alarms that they are, if you think for a second when there was the slow freezing methodology, you were comfortable, right, in using the machine that was doing it for you. You were not doing the slow freezing manually. And you are okay with that. So we probably will reach the same level of comfort and confidence even with the automatic vitrification. But, of course, you need much more numbers, much more experimentation. There are alarms, beeps that they alert the embryologists. But in the meantime, if you say, well, if I understood the principle, and the principle is to go 5 eggs at a time or 4 eggs at a time, whatever you need to do, all at once, not moving the eggs one at a time in different place, or whether you do the bridging or you do whatever, you still need to move the eggs. Now you don't need to move the eggs one at a time. So you are eliminating some of the potential variable. You can use the easy bit, the E-bit. Just do it by hand, and then you can also see, because embryology sometimes they are very uncomfortable when they don't see what's going on, and everything has to be trusted. Okay, now you can see through the transparencies of the straw, and you don't lose the control on that.
One last comment from Dr.
Anna.
Cobo.
Thank you, Pasquale, for your talk. I have a technical question. When the program is complete, give you the alarm that
Oh, that is finished, yeah.
how do you remove the sample from the put nitrogen container to do your storage?
To put it in your tank, yes.
You need to remove this and expose the sample?
No, there is a box. I mean, there is a box where the cartridge goes into the box that is full with liquid nitrogen, and then under the liquid nitrogen, one by one, you pour, yes. No, never exposed to the air.
Okay.
Yeah.
Well, thank you very much for the nice lecture and a very